This is part 12 of the series Integration. And in this section, we're going to be working with the antiderivatives of composite functions. Remember that a composite function could be something as simple as something like this, where you had some inner function and some outer function, something inside being raised to the second power. So that's what we're dealing with when we're talking about composites. So when we start working with antiderivatives of composite functions, we're getting into a process that's very highly visual and very highly pattern recognition oriented. You remember back in the days of derivatives, we were very process oriented. It was fairly easy to determine that a polynomial we had to apply the power rule to, or the constant multiple rule, or if we even saw a rational function, that we were going to have to use the quotient rule. It wasn't until we got to the chain rule that our visual pattern recognition skills became more important. And now that we're involved in antidifferentiation and integration, pattern recognition skills are going to become crucial. We're going to have some processes that we're going to have to apply, but the bulk of our skill set is going to be recognizing what it is that I'm supposed to do with a particular function at this point, and seeing if I can see a pattern that matches some process that I'm going to have to apply. So the first thing we're going to be dealing with here is how to differentiate a composite function. So let's dig in. Let G be a function whose range is an interval I, and let F be a function that is continuous on I. Now I think that first sentence needs some clarification before we move on. So here we have some function f that is a composite of some other function g. Now, in dealing with composite functions, this inner function has an output, which is its range. The output of that inner function has to be within the domain of f. And because we're dealing with antidifferentiation, integrability comes into play, and therefore continuity. So this function must be continuous on the output range of g. And so that's what this is talking about, that this function f has to be continuous on the output of g, the range of g. So moving on, if g is differentiable on its domain, and big F is an antiderivative of f on that same interval I, then we have the integral of f of g of x, the composite of f with g of x, times the derivative of g of x with respect to x, is equal to the antiderivative of f evaluated at g of x, plus some constant of integration. So this expression is defining a pattern that we're going to have to look for. If you have a composite of f and g of x multiplied by the derivative of the inside piece, that is your pattern that you're looking for. And the result, your answer, can be derived by taking the antiderivative of the outside function f with the inside function intact, adding some constant of integration. Now, there's going to be another process that's involved here that's going to be very, very helpful for us. And we're going to call this U substitution, where you can take your g of x, the inside function, and assign that to u arbitrarily. And taking the derivative of both sides, you would have du, the derivative of u, equals the derivative of g with respect to x. This is the differential form of the derivative of g of x. And you can then make a substitution. You can replace this g of x with that u, and replace the g prime of x dx here with your du here. And so this integral becomes the integral of f of u du equals the antiderivative of f evaluated at u plus our constant of integration. We're going to go ahead and work several examples, so hopefully this concept, if it's confusing at this point, it'll straighten itself out as we work through some examples and you see this in practice. So let's work the first example. So in this problem, we're trying to do the integral of x squared plus 1 squared times 2x dx. Now what we're looking for is this pattern where we have some inside function and some outside function being multiplied by the derivative of the inside function. So the first question you ask yourself, is this the derivative of this inside piece? And once you get more experience with derivatives and taking different derivatives, you'll be able to recognize these fairly quickly. That yes, in fact, this is the derivative of this, so we have our pattern. So I'm going to set my u to be the inside piece, the inside function. So u equals x squared plus 1. And then I'm going to take the derivative of this. So du equals 2x dx. And now you can see we have our pattern. Here, this x squared plus 1 can be replaced with our u, and this 2x dx can be replaced with du. So I can go ahead and rewrite this integral. I'm going to rewrite it down here, that we have the integral of u squared, because we replaced the u, but we still have the squared term out here. The 2x dx is replaced with the du here, so du. Now let's go ahead and take our integral. We know how to do this one. It is simply u to the third over 3 plus c. And now we'll back substitute our u into the final expression, and we have x squared plus 1 to the third over 3 plus c. It wasn't explicitly necessary to do this u substitution. You could have looked in here and said, oh, I can see that we have our pattern, so I know that my antiderivative is simply going to be the antiderivative of the outside, which is the something to the third over 3, and that piece is going to remain intact inside. But I want to introduce it early. If you get used to doing this and practice it over enough, it'll become automatic for you, and when you get to complex functions that require it, then it won't be such a chore. So I'm going to use this on everything that we can, just so that we get used to using it. So let's go on to the next problem. Now here we have a trigonometric function, and there is our inside piece. It's not this, it's this. So cosine is composited with 5x. So let's let our u be 5x. So u equals 5x. du equals 5 dx. And does this match the pattern? Well, yes, we have a u here, and 5 dx is right here. Doesn't matter whether you put the 5 here or over here, it still works the same way. Whether the cosine comes first or the 5 comes first, it's inconsequential. So what we have then is the integral of cosine u du. And the integral of cosine is sine u plus c. Back substitute, we have sine of 5x plus c. Let's move on to the next problem. So here we see we have an inner function here. So let's let our u be x squared plus 1. So u equals x squared plus 1. Differentiate. Du equals 2x dx. Now it appears we have a little bit of an issue, don't we? Because in this case we have an x dx. This u is fine to match this, but here we have an x dx, and down here we have a 2x dx. What we need is x dx, so we've got to get rid of this 2. So what I'm going to do is divide both sides by 2. So we have du over 2 equals x dx. And now we have a pattern match. We have our x dx, and we have our u and our du. So there's our u going here and x dx. So let's see how this works out. So we have the integral of u squared du over 2, because we had du over 2. Now this is just a concept where it's just 1/2 this whole thing, and we can use the constant rule to pull out the 1/2. So we end up having 1/2 the integral of u squared du. And now we just take our antiderivative. 1/2 times u to the third over 3 plus c. When we pull this together, we end up having our back substitution for our u gives us x squared plus 1 to the third. 2 times 3 is 6 plus c. So this 2 threw us for a little bit of a spin, but it wasn't too bad. Let's move on to the next problem. So here we have our basic rational function. So we're going to set u to be the radicand, 2x minus 1. Our du is 2 dx. Again, we have the superfluous 2 because we're just matching a dx. We have nothing else with it. So we're going to divide out that 2. So du over 2 equals dx. Now we have our pattern. We have our dx and we have our u. So this becomes the integral of u, and I'm going to rewrite this as a power, so a rational exponent, 1/2 du over 2. And again, we have a multiple of 1/2 here, so let's get that 1/2 out front. So we have 1/2 the integral of u to the 1/2 du. This becomes 1/2 u, add 1, 3/2 over 3/2 plus c. And I'm just going to go over here. And we have, this is going to flip. So I'm changing this to multiplication by flipping this. So we have 1/2 2/3, and I'm going to back substitute my u in here at this point. 2x minus 1 to the 3/2 plus c. And these 2's will cancel out. So in the final analysis, we'll have 1/3 2x minus 1 to the 3/2 plus c. And now let's move on to the next problem.